For today's optimal binary search tree, we have already seen that binary search tree is a type of tree in which the nodes on left side are smaller than root and nodes on right hand side are greater than or equal to the root. But again, even though we arrange our tree in this particular manner, there are multiple ways in which binary search tree can be drawn for given number of keys. And the way binary search tree is organized will impact on the searching cost of a tree. So why we go for optimal binary search tree is to reduce the searching cost, because the level of node and number of comparisons, these are two factors which will impact on calculating searching cost of overall tree. And we already have a formula to find out. If I give you n number of keys, how many binary search trees can be drawn. So it is 2ncn divided by n plus 1. So using this formula, we can simply find out how many binary search trees can be drawn from given number of keys. But now the question comes here is, if these many trees are possible, then we have to decide which tree out of these many trees is optimal binary search tree. Because every time for given number of keys, it is not possible to calculate the searching cost. It is not possible to represent it in all the ways we can have using the concept of binary search tree. So that's why optimal binary search tree is used to find out which particular organization of binary search tree will give us minimum searching cost for the given. Okay, so in optimal binary search tree, we are provided with number of keys, and then we know, as we are focusing on searching operation here, the basic focus will be on searching. So that's why searching can lead to two possibilities. Either our search will be successful, or if that number or key is not present in a tree, then we say that search is unsuccessful. So in optimal binary search tree, we are provided with number of keys, possibly with their names, and P is probability of successful search and Q represents probability of unsuccessful search. So here we have to remember that probability of unsuccessful search is always one more than probability of successful search. So by giving this information as an input, we have to construct an OBST. Now we know that we have to calculate or compute cost of each of the nodes. So here, as by considering probability of unsuccessful search, we have to draw one matrix which is in the form of rows and columns. It represents the nodes, and now we have to calculate cost of each of them. So here I is representing rows and J is representing columns. So basically, first of all, here number of keys, they are given as 4, and this matrix would be of size 5 by 5 because we consider probability of unsuccessful search as well. So in the first step, we have to find out values of I and J for which the difference is 0. So these lines, they represent absolute difference. So J minus I, absolute difference is 0. We have to find out those pairs of I and J. So as shown in red color here, for these pairs like I equal to 0, J equal to 0, difference would be 0. Same way I1, J1, I2, J2, likewise I4, J4, difference would be 0. So likewise we have to find out all the pairs of J and I for which this difference is 0. So we have identified and we have marked their costs as 0. So what the formula says, initially in first step, whenever values of J and I are same, how weight is calculated? So in this case, weight is directly assigned to probability of unsuccessful search. See, in problem statement, we are given with probability of unsuccessful search. So here we can simply write W of Ij equal to Q of I. We can also replace J with I here because here ultimately I and J is same. So instead of writing W of Ij, I have written it as W of II equal to Q of I. So this value is directly assigned. and cost and this root values, they will remain 0 when I and j absolute difference is 0. So here W of 0 0 would be equal to Q of 0. So we can see here Q of 0 is what? 2. Q of 1 is 3. Q of 2 is 1, and likewise Q of 4 is 1. So this particular values, they are already given in problem statement, and same values we have to assign to it. So W of 0 0 will be equal to Q of 0, that is equal to 2, and cost and root values will remain 0. W of 1 1 will be equal to Q of 1, so that is equal to 3, and yes, remaining values will be calculated in the same way. Anyway, cost and root are going to be 0 for all. Only weight values will be assigned with values which are already specified in the probability of unsuccessful search. So this is our step number 1, where we have taken all the pairs of I and j where absolute difference was 0. Now in the next step, we have to take all pairs of j and I where absolute difference is 1. Now this step onwards, we will be using these 3 formulas for calculating weight, cost and root value. So how weight is calculated? W of ij equal to W of I comma j minus 1 plus P of j plus Q of j. So P of j is probability of successful search, which is given in the problem statement. Q of j is probability of unsuccessful search. So this is also given in the problem statement. Now how this cost of ij is calculated? So this is minimum of these two values. So minimum of C of I comma k minus 1 plus C of k comma j, and then this value is added with weight of ij. So here in curly bracket we have to find out for which value of k we are getting minimum cost. Okay, so here we have to change the value of k, and we can see here k is greater than I, but it is smaller than or equal to j. So you can say that k is equal to I plus 1 and k is less than equal to j. And then the value of k, which is giving us minimum cost, will be assigned as it is directly to the root. So this k value is then copied into R of ij. But for this k value, we should ensure that the cost is minimum. Let's start with computations. So W of ij. So W of ij, now we know the absolute difference should be 1. So we can easily see here in the matrix. So for this particular diagonal, absolute difference was 0. Now if we go one step up, like I have to go with this diagonal now. Earlier I had 5 values, 5 pairs of I and j where difference was 0. Now if I go to one level up, I will have only 4 values for I and j where absolute difference is 1. Likewise, if I move one step ahead, I will have only 3 values of I and j where absolute difference will be 2. Just follow my mouse pointer and see. Then if I go one more level up, then there will be only 2 values, 2 nodes for which absolute difference of I and j is 3. And at the end I have only one value where absolute difference of I and j is 4. So this is how we have to go with calculations. So W of 0 1 equal to W of I is equal to 0. This is j value, second parameter is j, so we have to subtract 1 from j, so this will give me 0. So W of 0 0 plus P of j, so j here is 1, so P of 1 plus Q of 1. So we know W of 0 0 is directly probability of unsuccessful search, that is Q of 0, already we have calculated, this is 2 plus P of 1 already given in problem statement, that is 3 plus Q of 1 is also 3, which is giving us value 8. So weight is 8. Now next, see how cost is calculated. So we are using same formula, just substitute values of I and k and j. So here we can see that what value we should keep for k. So here this is I and this is j. As I said, k will be greater than I but smaller than or equal to j. Now j have only one value, that is 1. So k must be greater than 0 but less than or equal to 1, so it cannot be fractional. So it is clear that k can have only one possible value, that is 1. So if I substitute 1 here in the formula, it will be C of 0 0 plus C of 1 1, and we know whenever I and j values are same, cost is always 0. So this will be 0 plus 0, that is 0 itself. And W of 0, 1 we have just calculated, that is 8. So minimum of 0 plus 0 is 0, that will be added with 8, and here we get cost of 0, 1 as 8. Now as we have only one possible value of k, that is 1, so here this k value, that is 1, is assigned to r of 0, 1. So r of 0, 1 here is 1. In very similar way we calculate w of 1, 2. We can see here again difference between I and j is 1. So again cost will be calculated, and even for which value of k we are getting minimum cost, that is identified, and that value is assigned to root. Next you will go for another pair where absolute difference is 1, w of 2, 3, calculate cost and calculate root value, and again at the end you will have w of 3, 4 where absolute difference is 1. So again substitute these values of I and j in the given formula, calculate cost, and yes, so for which value of k we are getting minimum cost, so that is 3. So here we have to substitute, we have to assign that value of k to r of 3, 4. So this is how we have done with step number 2, where we have taken all pairs of I, j where absolute difference was 1. Now we have to consider all pairs of I and j where absolute difference is 2. So we can see the first pair here is w of 0, 2. So again this is I and this is j, and formula what it says, w of I comma j minus 1. So 2 minus 1, that is 1. Weight of 0, 1 is already calculated in the previous step. So that is 8 taken as it is. Then p of 2 plus q of 2. So these values are already specified in the problem statement where probabilities of successful and unsuccessful search are given. So this is how 8 plus 3 plus 1 evaluates to 12. And now coming to the cost. Now here we can see that I value is 0 and j value is 2. So possible values of k would be 1 and 2, because k should be greater than I but less than or equal to j. So now first of all we fill k equal to 1 in the given formula and then find out the cost is 7. But when I fill value of k as 2, I am getting cost as 8. So out of 7 and 8, which one is minimum? 7. So we choose 7 plus w of 0, 2, that is already calculated, that is 12. So we add 7 plus 12 gives us 19. And for which value of k we have got this 19 cost? This is for k equal to 1. So here we assign k equal to 1 to r of 0, 2. In very similar way, w of 1, 3, cost of 1, 3 is calculated, and so on. So remaining pairs where absolute difference is 2, again w of 2, 4, c of 2, 4 and root of 2, 4 is calculated. Now yes, the thing to remember here is, if we are getting same cost, now see here we can see when we put k equal to 3, there also we are getting 3 cost. When we put k equal to 4, there also we are getting same cost. In this case, it is okay if you put k equal to 3 or k equal to 4 for r of 2, 4. So either we can take 3 or we can take 4. That's not the problem. And then now the step number next, where we have to consider values of j and I where absolute difference is 3, and again same thing. So the thing to note here is that whenever j and I absolute difference is 3, there will be 3 possible values of k, 1, 2 and 3. So yes, we have to substitute these 3 values in the cost formula, and we have to find out for which value of k we are getting minimum cost. So here it is 12, 8 plus 3, 11 and 19 plus 0. So 11 is minimum. For which value of k we have got it? We have got it for k equal to 2. So yes, we choose k equal to 2 and assign it to r of 0, 3 and so on. So in same way we will be calculating w of 1, 4, c of 1, 4 and r of 1, 4. And at the end we are left with pairs of I and j where absolute difference is 4. So we have only one pair, w of 0, 4. So for this pair we substitute values into the formula and we calculate the cost as well. So Whenever absolute difference is 4, of course there will be 4 possible values of k, and we have to find out for which possible values of k we are getting minimum cost. So here 8 plus 8 gives us 16, which is minimum amongst this, and that's why 16 is added with w of 04, which is recently calculated, that is 16 equal to 32, and r of 04, for which value of k we have got this cost 16, so that is for k equal to 2, so r of 04 here is 2. So we substitute these values in formula, and yes, we have came up with this particular matrix. I can say this is upper triangular matrix where we have calculated cost of each of the node. And now the question remains where we have to draw the tree, final binary, optimal binary search tree. So how do we do that? R of ij equal to k is taken as root. On the left side, r of I k comma k minus 1, r of I comma k minus 1, and on the right hand side we have r of k comma j. So if we substitute this r, the last value we have to take as a root always. So r of 04 equal to 2. So here I is 0, j is 4, and k is 2. Okay. Left hand side, again this is I comma k minus 1. So what is k here? 2. 2 minus 1, 1. R of 1 equal to 1. And just go on substituting the values unless we get I and j as equal. That means they are leaf nodes. Okay. And once we expand our tree like this, so this indicates that key number 2 will be our root. So the keys in the problem statements were do, if, int, and while. So this is key number 1, 2, 3, 4. So which is key number 2? If. So if will be our root. If left is key number 1. So if left will be do, we can see here. Then next is r of 2, 4 equal to 4. So key number 4. Okay. Here key number 4 will be there on this particular side. We know r of 2, 4 has two values, either 3 or 4. So already we have seen we can either take 3 or 4. So I have shown both the trees here. We can also take third key, that is integer, on the right hand side of if, or we can also take while. Okay. So that's not the problem. And if I take integer here, then we know if I take integer here, that is third key, then the fourth key should be there on the right hand side. So here we can see r of 3 comma 4 is 4. So fourth key will be there on the right hand side. And if I take while here, that is fourth key, then we can see 4 left is 3 here. So 4 is while, and while left is third key, that is integer. So this is how final optimal binary search tree can be drawn.